This conference will now be recorded.
Last day we have started D and A block elements, and some of the properties already we have discussed. Today we will see enthalpy of atomization, and after that there will be discussion related to trend in melting point and boiling point, how it is changing, and then trends in different oxidation state, and also the electrode potential values and related problems. Now, enthalpy of atomization, this property is something new because we have not discussed this property in other groups. That is, I'm talking about P block elements, there we have not discussed it. But why we are discussing it here? Because D block elements mainly containing metals. And for metals, enthalpy of atomization, this term is important. And it has direct relation to the trend in melting point and boiling point variation. So, if we want to understand how melting point and boiling points are changing, so basically we have to understand enthalpy of atomization. So that is why before the discussion of melting point and boiling point, we should have proper idea about the enthalpy of atomization. Okay. Now, enthalpy of atomization, what is the definition in general, not just for D block elements. In general, what is enthalpy of atomization, that we have to know first. So enthalpy of atomization, it is the change in enthalpy. Obviously, it is enthalpy. It is a change in enthalpy when 1 mole of bonds is completely broken to obtain atoms in the gas phase. So here we have taken CH4, that is methane, and if it is broken, all the bonds are broken, you will be getting 1 carbon atom and 4 hydrogen. And the corresponding enthalpy change is 1665.0 kilojoule per mole. Okay, so this is the definition of enthalpy of atomization. Now we will come back to D block elements. For D block elements, enthalpy of atomization, it is linked to the strength of the metallic bonds. Now here we will talk about metallic bonds because D block elements are mainly metals. Okay, so that is why the question of metallic bonding arises. So metallic bonds are basically what happens. I will here describe a primary idea about the metallic bond. There are different types of bond: ionic bond, covalent bond, polar covalent bond, and metallic bond, which is specifically for metals. Now metals, suppose when they are neutral, suppose M like this, but if they are losing electron, so there are different M plus centers, and for each M plus there will be an electron. Now which electron is coming from which M plus, here that is not fixed. So as if all these M plus moiety, they are floating in the sea of electrons. So this is metallic bonding. Okay. And enthalpy of atomization, this is directly linked with the strength of metallic bond. So if we want to know whether metallic bond strength is high or low in these D block elements, we have to know what is the enthalpy of atomization. And remember, in case of metals, we also consider enthalpy of atomization. There is another name for it, which is enthalpy of sublimation. So just take that is this example, it is given for methane molecule. But when we are talking about metallic bond, just take the example of copper. It is neutral, right? But suppose it is copper plus and it is in solid state. But when it is converted in gaseous state, so this is actually the enthalpy of atomization. Okay, and remember, it is also called enthalpy of sublimation. Now, transition metals, they will have higher enthalpies of atomization because of two reasons. First is presence of large number of valence electrons. So as I have said that metallic bonds, whenever we are considering, so there will be a sea of electrons, and as if the M plus, it is floating in the sea of electrons. So this is the first reason, the presence of large number of valence electrons. And the second one is high effective nuclear charge. So because of these two reasons, here high enthalpy of atomization values are observed for transition metals. Now in D block elements, if you consider any particular group, okay, so just consider group 3, fine. So there is first series, which is 3D element, then 4D, and then 5D. Now 4D and 5D transition metals in the same group, they will have larger size compared to 3D because we are moving down. Now when size is increasing, the valence electrons are less tightly held, and as a result, metal-metal bond formation, it will be very facile. So it can easily form metal-metal bond. Fine. So that is the reason if we consider any particular group in D block, and when you are moving down, that means from 3D you are moving to 4D, then you are moving to 5D. So as we are moving down from 3D to 4D to 5D, then enthalpies of atomization will be high. So down the group, the value will be increasing than those of 3D series. So that is the reason. Obviously, you can expect that melting point, boiling point, both will also be high as we are moving down. And because of this high enthalpy of atomization, sometimes you will see, though it is this type of example in D block we will not discuss, but still you will see as you are moving down, metal-metal bonds like this. It may be triple bond, sometimes 4 bonds are also possible. So this type of bond you will not see in case of 3D, that is the first series. But as you are moving down, this type of metal-metal multiple bonds, they are very common. Okay. Now why it is common? Because metal-metal bond formation tendency is increasing down the group because enthalpy of atomization that is also increasing. Here we have a graph which is having y in the y-axis there is enthalpy of atomization in kilojoule per mole, and in the x-axis we have groups. So starting from group 3, it is ending at 12, which is all the groups in D block. Now the blue line, this is for 3D, then the green one, that is for 4D, and the last one red, that is for 5D. So see, as we are moving down, basically in the graph you can see the values are increasing. So for any particular group, suppose consider group 9. So see, first the lowest value for enthalpy of atomization, this is for 3D, then for green line which is for 4D, and then for 5D. Okay, and here in blue line there is sudden decrease at group 7, which is basically manganese. And why it is so? Because here enthalpy of atomization, there is drastic decrease, and it is because of the that is, remember the configuration, it is 3d5 4s2. Okay, so when 2 electrons are removed, there will be stable half field configuration which is very stable. So because of that reason, here enthalpy of atomization, there is a sudden change, and minimum values, this is for Mn and also for the last group, that is zinc. Okay, but this is a trend, and from this trend, because here all the series are present, you can compare that how down the group enthalpy of atomization is increasing. Any doubt? So after enthalpy of atomization, now we will see melting and boiling point trend. So these two are directly related. So that is why when you will see the melting point and boiling point, you will find some similarity. So in this graph, here we have only the first transition series, but here the red line, that is for boiling point, and the blue line, that is for melting point. And here temperature in the y-axis are given. So if you consider any particular point, just draw a line on the y-axis, you will get the corresponding value of temperature in the y-axis. The melting points and the molar enthalpies of fusion of the transition metals are both high when we compare with the main group elements. So main group elements, just take S block, you will see this type of high temperature. Look at the values, these are very high, right? So this type of high temperature you will hardly see. So that is, it is mentioned that melting points and molar enthalpies of fusion, that is from solid state, now it is converted to liquid state. This temperature that is required, this is very high. Now the reason is strong metallic bonding that is present in case of 3D elements and not present in case of other main group elements. So this strong metallic bonding in transition metals, which occurs because of delocalization of electrons, and that is facilitated by the availability of both D and S electrons. Okay, if you consider any other group that is in S and P block, there is that is just simply take S block. So there is valence electron only in S, or in P there is valence electron only in P orbital. But in this case we have both D electron, S electron. So that is why electrons are available, and as electrons are available, strong metallic bonding is present, and because of this strong metallic bonding, melting point also is very high compared to main group elements. So from this graph it is clear, because all these values are almost, that is around either 1500 or more than that. Okay, so this is very high value. Another graph also we have, which is only for melting point, but we have total 3 lines, and the first line that is for 3D, then the blue line that is for 4D, and the last line that is for 5D. Now in the previous slide you have just seen the atomization, enthalpy of atomization, how it is changing for the 3 series, 3D, 4D, 5D. And see, you will find it that the nature of the curve, it is almost same as you are seeing here, that is in case of melting point. Now it proves that this melting point trend and enthalpy of atomization, these two trend, that is the nature of the curve, is almost same. So which proves that these two are highly correlated to each other. When enthalpy of atomization high, melting point is also high. Now just have a look in this graph, and that is I'm talking about this graph where all these 3 series are present together, and also see this curve, which is the enthalpy of atomization curve. So both these curves, there is so much similarity, right? But it is melting point, the previous one that is enthalpy, so it is energy, joule unit is there, but now it is Kelvin. Now here also melting point, as we are moving down, that is when you are switching from 3D to 4D to 5D, gradually the values are increasing. Okay, now that is expected because down the groove atomization, that is enthalpy atomization, that is also very high. Fine. Now in the group 12, the first element is Zn, then cadmium, then mercury. Now these metals, they will have very low MP and BP. See, all these 3, they are very low. That is compared to other elements, they are very, very low. Now why it is so? Because of unavailability of unpaired electron. Because the configuration of Zn, if you see, it is 3D10 4s2. So you cannot find any unpaired electron. So all these electrons are paired. This is fully filled configuration, and in 4s2 this is also paired electron. So because of the absence of this unpaired electron, metallic bonding will be very weak. So you can easily melt them from solid state to liquid state. So that is the reason here for these 3, that is group 12, all are having very low MP and BP. They do not undergo covalent bonding. That is all about metallic bond. So this ZnCdHg, as metallic bonding is very, very poor, and also they are not undergoing covalent bonding. So overall effect is MP and BP all are very low. Rest of the elements, that is except these 3, rest of the elements you can find covalent bonding also. That is not just metallic bonding, there is also presence of covalent bonding. So in this way, melting point and boiling point, both are related to, that is the trend in MP and BP, these are related to the trend in enthalpy of atomization. And we have also seen it, how down the group the values are increasing. So is there any doubt? Should I repeat any part? Next is oxidation state. Transition metals, if we compare with other block, S block or P block. In S block, what we see, suppose if it is group 1, there is only one oxidation state which is fixed, and that is +1 oxidation state. You will not find any other oxidation state. Lithium plus, sodium plus, potassium plus. Similarly, if you consider group 2, only one oxidation state, +2, that is magnesium 2 plus, calcium 2 plus. Similarly, when you move to P block, which we have just finished, that is before this starting this D block chapter, there also we have seen that for each group, because there are total 6 group, 13 up to 18. So for each group there is a fixed oxidation state, and except this fixed oxidation state, there are some other oxidation states present. But this type of variation, as you can see in this table, which is for 3D series, an oxidation state variation, it is so high, okay, and there is no general trend also that is present. Now, unlike this S block and P block, now you can see variable oxidation states are possible. Okay, so this is a unique property which we do not see in other elements. All the elements show variable oxidation state, and that depends upon the number of electrons available for bonding in s orbital as well as d subshell. Just take example of scandium. Scandium is 3d1 4s2. So when you are removing 2 electron from 4s, you are getting oxidation state +2. After that, if you are also removing the single electron from 3d, then you will get +3. So in this way, these 2 oxidation states possible. Now when you move to titanium, it is 3d to 4s2. That means now you have total 4 electrons. So first, when you are removing 2 electrons from 4s, you are getting +2 oxidation state. Then you are removing third electron, it is +3, and when you are removing all the electrons, it is +2. So in this way, oxidation state will depend on the availability of how many electrons are present in S and D subshell. Now, here electron removal possible both from 4s and 3d, which is also unique. That is what we see in S block. In S block, we are just removing electron from S orbital. In P block, we are just removing from P orbital. But now we are removing D as well as S. And why it is so? Why it is possible? It is because of the low energy gap between the D and S. So when it is fast transition series, you have 3D and you have 4s. So 3D and 4s, these two will be very close in energy. Same thing is also true when you are moving to second transition series. That is presence of 4D and 5s. And the last series, presence of 6s and 5d. So the energy levels, that is 3d and energy level 4s, they are very close to each other. That means energy difference is very low. So electrons can be removed from S as well as from D. This is the reason. Therefore, electrons from both Ns and N-1d. So all these are Ns and all these are N-1d, right? Any doubt? So all these 2 types of electrons can take part in bonding, and that is the reason so much radiation is possible. Now when if you look carefully in this table, when you are reaching in the middle zone, that is if you focus on this part, maximum oxidation states are present here, right? And maximum in the first series, it is for Mn. See how many oxidation states? Total 6 oxidation states possible. Now for the element starting from scandium up to Mn, highest oxidation state. That means for scandium, what is the highest oxidation state? It is +3. Then for titanium, this is the +4. For vanadium +5. Then +6 up to Mn +7. So here it is mentioned that highest oxidation state starting from scandium up to manganese, it corresponds to the loss of all the electrons in both S and D. So this highest oxidation state, how you can achieve? When you are removing all the available electrons, right? Now after Mn, when you are having Fe, now Fe is 3d6 4s2. That means 8 electrons available. But see here, highest oxidation state is not +8, it is +6. That means only up to Mn, maximum oxidation state, it directly corresponds to the loss of all the available electrons. That is electrons both from S and D. But after manganese, this is not the case. The highest oxidation state are most stable forms for these three elements. Okay, but why after Mn you are not getting +8 oxidation state? Because now pairing will start. Up to Mn you have 5 unpaired electron, but when you are moving from 3d5 to 3d6, now one pairing will occur, and to break the pair it is difficult process. And if you are not breaking the pair, +8 oxidation state from iron you cannot get. So that is the reason, as pairing now it is starting. So that is the reason we cannot remove all the electrons. However, it is not possible to continue to remove all the valence electrons from metals as we continue through the series. So this is the statement that I have just said. Now see, when you are moving from iron to cobalt, now you have two paired electrons. So that is why that pair you cannot break. Now when you are reaching nickel, similarly same thing. When you are reaching copper, now the configuration is 3d10 4s1. And when you are removing this single electron, you are having +1, and second electron, now you have to break the pair. So that is the reason, that is +2 you can get only when you are removing electron from D, but you have to break the pair. So that is the reason, as we are moving from left hand side to right hand side, gradually pairing is increased, and as you have to break the pair, which is difficult process, so gradually the number of oxidation state, that is also decreased. Okay, so is it clear why in the middle zone maximum oxidation states are possible? Is there any doubt? Because this is an important question, that in the series from scandium group 3 up to Zn group 12, why maximum oxidation state it is possible only in the middle zone, especially for manganese, because that is at the middle point, right? So is it clear? Now we will also see oxidation state for the other two series. Now other two series also, when you are reaching in the middle zone, you can see maximum variation is possible. The element of the second and third transition series, second is 40 and this is 5D. The elements of these two transition series generally are more stable when you are considering higher oxidation state. That means higher oxidation state availability, that is more in case of these two series compared to first series. For example, if you consider group 6, now group 6, what are the elements present? Chromium, then molybdenum, then tungsten. Chromium from first series, 3D series, then 4D, then 5D. Now molybdenum and tungsten, that is W, they are limited mostly to oxidation state +6 when you are considering aqueous solution. So in aqueous solution, molybdenum 6 plus, W 6 plus, all these are stable. But chromium, which is also in the same group, but it is the first member, that is lightest member of the group, it can form stable chromium 3 plus ion in water. And if it is absence of air, then less stable Cr2 plus ions formation possible. But see, in case of molybdenum and tungsten, you can get easily +6, but for chromium you are getting +3. That means high oxide, though they are from same group, but as you are moving down, high oxidation state will be more stable. It is in water, and chromium 2 plus, that is in absence of air, because absence of air means absence of oxygen, and when absence of oxygen means oxidation of Cr2 plus is not possible. But if it is in presence of air, then in presence of oxygen, chromium 2 plus, it can lose electron and it can be converted to 3. That means oxidation is possible. Then another example, sulfite with the highest oxidation state for chromium is, that is if you consider sulfite compound, that is compounds of sulfur, then for chromium +3 oxidation state is possible. But if it is molybdenum and tungsten, that is the other members of the same group, they can also form sulfide, but now they can form sulfide with higher oxidation state, which is 4 plus and 6 plus. So see, first example we have seen that in aqueous solution how they will behave. In aqueous solution, chromium is having plus 3, but the other two members, they can have plus 6. Similarly, when it is sulfide compound, it is plus 3, but they can have plus 4 and plus 6. So it proves that as we are moving down, higher oxidation state will be more stable. Okay, any doubt? So if it is asked that considering 3D, 4D, 5D series, what is the maximum oxidation state that is found? So it is plus 8, which you can see for ruthenium as well as for osmium. So ruthenium and osmium, they are in the same line with iron. Fe, then ruthenium, then osmium. Now in first series, 3D series, what is the maximum oxidation state possible? It is plus 7, that you can see only in case of manganese. But for these two series, plus 8. Now this is a known highest oxidation state that is observed. But as research is going on, there is some recent findings which says that iridium in plus 9 state, that is also found recently. 2014, researchers were successful in synthesizing a new oxidation state. So this is just reported, newly reported. So maybe in future some other oxidation state that will also be discovered. But until now, this is the information that we have in our hand. Okay. Now we have a problem regarding the oxidation state of transition metals. Here we have three compounds. The first one is chromium compound, then manganese compound, and iron. And all these are potassium salt, and oxygen is also present. You have to find out the oxidation state of these three transition metal, chromium, manganese, iron, respectively, and the oxidation states are X, Y, and Z. This is X, this is Y, and this is Z. And after that, you have to add all these numbers and you have to find the value. So basically, it is an integer type of problem. Okay. Now consider the first compound, which is K2Cr2O7 potassium dichromate, 2 potassium ion. That means 2 positive charge. So 2 plus X, but X multiplied by 2 because 2 chromium. Now for oxygen, each oxygen minus 2, so it will be 7 into minus 2. Overall the molecule is neutral, so it is 0. So the value of X is 14 minus 2 divided by 2. That means plus 6. X value is plus 6. Then the second compound, KMnO4, 1 for potassium, manganese is Y, and for 4 oxygen it will be 4 into minus 2. Overall molecule is neutral, so Y will be equal to 8 minus 1, that is plus. Similarly, you can do the calculation for K2FeO4, 2 potassium, Z, 4 oxygen. Now can you tell me what will be the oxidation state for iron in the last compound? Overall it is 0. What is the value of Z? What is the value of Z? Because after finding it, we have to consider addition. That is, we have to add all the numbers. So what is the value of Z? Eight minus 2 plus 6. That means 6, 7, and then again 7. So if you add these three numbers, you will be getting 19. Any doubt?
No, ma'am.
The set that contains atomic numbers of only transition element. So there are total 4 options, 4 set. So all these numbers are basically atomic numbers. Now when I have discussed electronic configuration for D block elements, then I have mentioned one trick. Though you can easily memorize and you can find the answer, but one trick that you can apply. So suppose if you consider the element from first series, and if it is having oxidation state, just take example of scandium. So it is having atomic number 21. So when you are moving from first series to second series, you have to add 18. That means 21 plus 18, and 21 plus 18, it will be 39. Now if you are now moving from second series to third series, again you have to add 18. So in this way, if you are able to remember the atomic number of the first series, then just by adding 18 two times, you can get the number for the other two members of the same group. But this addition of plus 18 two times, as you are moving from 3D to 4D, then again from 4D to 5D, this is only for the first group, that is group number 3. But if you are now moving to group number 4, that is next element titanium, which is having oxidation state 22. Okay, so 22, and you are moving to the next member, you have to add 18, so it will be 40. Now when you are moving from 4D to 5D, now you have to add 32. Why? Because there is 4A block present in this position, so that is the reason. Now you have to add 32, not 18. So this I have already mentioned during the discussion of electronic configuration. So in 4F, maximum capacity is 14. So now that is why 18 plus 14, it will be 32. So if you want to get the next number, you have to add 32, and it will be 72. So in this way, you can find in the same group, you can find out the atomic number. Now here, if we look at the options, 37, 42, 50, 64. Now none of this number, it is in the first transition series. But so if you are able to remember only the first series, that is starting from 21, which is for scandium, up to Za, ending at atomic number 30. So from 21 to 30, none of these numbers are present here. So there may be, it may be from 3D, the other two series, that is 4D series and 5D series. But if you look at the option B, it will be easier for you to understand, because 21, it is for scandium, that we can remember, okay, because it is from first series. Then 25, it is for manganese. Now the next number, which is 42, just subtract 18 from 42. So if you are getting any number which is matching with the atomic number of first series, then it will prove that 42 is transition element atomic number. So 42 minus 18, it is 24. Now 24 is the atomic number of chromium. That means 42, that will be in the same line of chromium. Similarly, if you consider 72, suppose you are subtracting 18, what you will be getting? 54. Another thing also you can do, you can subtract 32, 40. Okay, so if it is 40, next you are subtracting 18, you are getting 22. Now 22, it is the number of titanium. That means 72, it is in the same line of titanium. Isn't it? Try to understand. So it will be from 5D series, because subtracting 32, the number that you are getting, it is for 4D series, and then when you are subtracting 18, you are getting 22, which is for titanium. Now look at this periodic table. It is basically memory based, but some tricks you can apply. So this is 21, then 25, 42, but 42 how we have obtained? By subtracting 18, and what we have found? 24. That means 42 will be in the same line of chromium, molybdenum. Okay, and 72 how we have obtained it? By subtracting 32 and then 18. So see, 72, that is actually halfway. So when you subtract 32, you will be getting 40. And when you are subtracting again 18, you are getting the number 22. So basically here option B will be the correct option. Okay, and option C you can easily understand it cannot be the correct option because 9 atomic number. This is for fluorine. Obviously, if one of the number is not for transition element, you can easily cancel that option. Okay, and 17 it is for chlorine. So these two easily proves that this cannot be the correct option. Okay, so in this way, applying some tricks, we can choose the correct option. So should I repeat this question once more? Next, trend in standard electrode potential. Now, as these elements are metallic in nature, and mostly when we consider electrode potential, it is mainly metal. So that is why they are trained in standard electrode potential. That also we have to know. In the measurement of a reduction potential means that how easily it can reduce some other species. And when the standard electrode potential values, if it is becoming more and more negative, that means reducing capacity is also very high. In the measurement of reduction potential, we are generally working with metal electrode in an aqueous solution of ions. So look at this picture. What we do, we take some metal electrode and we dip in the solution of that particular metal solution. That means if it is suppose copper electrode, then there will be copper 2+ ion in the solution. Okay. Now as it is in aqueous solution, these metal ions that will be surrounded by water molecules. So see, this is copper. If it is metal ion, this is surrounded by different water molecules. So it is not free metal ion. It is surrounded by different water molecules. Okay. And the delage value that will give us the enthalpy change which is required to bring the solid metal to the monovalent ion in aqueous medium. So solid metal is denoted by M, and when it is in aqueous solution, now it will lose electron, there will be some oxidation state, and also in the bracket you have to mention aqueous, which means it is surrounded by water molecules. But this conversion from solid metal to metal plus aqueous, this is actually involving some steps. So you can move directly from M to M plus aqueous, and the corresponding enthalpy change you can write as del H. But there are some other ways from which you can move from this state of metal solid to M plus aqueous. So suppose this is state number 1, this is state number 4. You can move from 1 to 4 directly, but there are other ways that also you can follow, which is first you move from metal state number 1 to state number 2, then state number 2 to state number 3, and then state number 3 to state number 4. And in these three, that is 1 to 2, 2 to 3, 3 to 4, suppose the corresponding enthalpy change, it is del H1, then del H2, then del H3. That means when you have moved directly from 1 to 4, this enthalpy change, del H, now this del H will be equal to del H1, del H2, and del H3. And this is based on Hess's law. And this type of relationship is possible only for state function. And enthalpy state function in thermodynamics, you know, it is state function. So that is the reason. State function means the value does not depend which path you are following. Okay, so whether you move from 1 to 4 directly or if you are for doing this via some other ways, in both cases, that is the net change that will be same. Okay, so that is the del H. It can be related to these three values in this way, summation. Now we will take particular example. Here we have, start from here. So suppose you have copper in solid state, C in bracket S is mentioned, and you are adding water. So this is your state number 1, and what you are getting now, you are getting metal plus aqueous. This is state number 4. So this is direct movement. Okay, dotted arrow is there. But if you are moving from 1 to 4 via some other ways, and what are those ways? First, you are converting Cu solid to Cu gaseous. So that is why here it is mentioned G, and the corresponding enthalpy change is enthalpy of sublimation. That is, it is mentioned del H SUB, enthalpy of sublimation. So this is step number 2, and the corresponding, there is some, this is the enthalpy change. This is here del H1 is basically del H sub. Then from copper gaseous, now you are removing electron by applying fast ionization energy, and now you are getting copper plus G. So this is step number 3. And in presence of water, now from copper plus gaseous, in presence of water, enthalpy changes enthalpy of hydration. Now from Cu plus gaseous, you are getting Cu plus aqueous. So this is the corresponding enthalpy change. This is also enthalpy, because enthalpy is also one form of energy, right? Ionization energy unit is kilojoule or joule per mole, and enthalpy, that is also joule. So same unit. So here it is written IE, ionization energy, but that is also enthalpy. Okay. So this enthalpy change when you are moving from 1 to 4, and when you are moving via 1 to 2, then 2 to 3, and then 3 to 4, there will be this relationship will be applicable. So see, del H is equal to, this is del H, that is equal to del H sublimation, ionization energy 1, and hydration enthalpy. Now suppose if it is metal 2 plus, in that case you have to apply second ionization energy also. So one extra term will be there. Okay. So electrode potential of metals, that will be decided by all these three enthalpy factors. The first enthalpy, when you are removing atoms from the electrode into the gas phase, that is copper S2, copper G. Then you are removing electron from that, so you have to apply ionization energy. Then what you are doing, you are solvating the resulting ion. That means from gaseous state, now you are bringing the ion to aqueous state. So you have to now provide hydration enthalpy. Okay. Now, if you are thinking that why we are discussing enthalpy, because the topic is trained in standard electrode potential, then why we are talking about del H? Now, del H and electrode potential, these two are have some relation. And what is the relation? See, when we have discussed electrochemistry chapter, there we have seen that del G is related to E by this relation NFE, where F is Faraday, N is number of electrons involved. Now del G is also related to enthalpy by the relation, which is very important relation in thermodynamics, that is del G is equal to del H minus T del S. That means del G is related to enthalpy, and del G is also related to E. That means electrode potential is also related to enthalpy. So that is why we are discussing this del H. Now this overall enthalpy, as it is related to standard electrode potential, and this del H is also dependent on these three individual enthalpy. So any of these three values, if there is up and down, that means overall del H it will be affected. Okay. Any doubt? So lower is the electrode potential value, that is more negative is the standard reduction potential SRP of the electrode, the more stable is the oxidation state of the transition metal. So suppose you have neutral metal and you are converting it to M2 plus. And for this, the value of the electrode potential, there will be some specific value. Now, when the value is very negative, suppose in one case the value is -1 and another case the value is -2. Now, which one is more negative? -2 is more negative. So, the metal for which the value is -2, in that case, this loss of electron by the metal and to achieve 2 plus state, this process will be very easy. That means it can easily donate electron. So its reducing capacity is very high. So lower is the reduction SRP value. I mean to say more negative the value is, more will be the reducing capacity and more stable will be the oxidation state, because this oxidation state is stable. That is why electron removal is so much easy. Okay. In the aqueous solution, obviously aqueous solution, metal can readily lose electron in that case and it can form cation very easily. That means itself, the metal itself is oxidized and it is reducing some other species. Fine. Now in this table you can see all different del H values are given. So here this data is in kilojoule per mole, all the enthalpy. For the first row transition elements, look at these metals, all are from first row. Standard electrode potential for the reduction of M2 plus to M. So normally when we write the equation, we write it in this way, that is M 2 plus accepting electron converted to M. Okay. And here for this reduction of M2 plus to M, that is for this process, all these are the del H values. And as here you have to remove 2 electrons, so that is why first ionization energy, second ionization energy, both are mentioned. Remember the first enthalpy, that is for sublimation. Just have a look in the previous. Here in this blue box, the first enthalpy, that is for conversion of metal from solid to gaseous. Then the second enthalpy, that is for ionization energy. If it is 1 electron, there will be 1 ionization energy. If it is 2 electron, there will be 2 ionization energy. If you are removing 3 electrons from metal to metal 3, then 3 ionization energy will be involved. And lastly, enthalpy of hydration. So that is, all these are mentioned in this table. This is for sublimation. These two are ionization energy and the last one is enthalpy of hydration. So mostly you will see that these values are positive. Look at this column. These 3 columns are positive and ionization energies are always positive, right? Because you have to have a supply energy. You are removing electron forcefully, so obviously you have to supply energy. But del H hydration, mostly these values are negative, because when it is hydrated, energy is liberated. It is exothermic process. Okay. And combining all these del H, there you will be getting some overall del H. And depending on this overall del H, there will be some del G. And depending on that del G, you will have some standard electrode potential. So these are the ultimate values that we have obtained. Now, if it is asked that why for titanium it is -1.63 and for zinc it is not so negative, right? Now, exactly what is the reason? Without looking at these values, you cannot get. You have to consider individual values. So suppose for titanium C, this is very high, but for zinc, this value is very low. But another value, that is ionization energy, now it is high, it is low. So all these values, there may be decrease or increase. And the combined effect you can see in the E0 value, which is in volt. Fine. So here we have a graph which is having in y-axis E0 values, x-axis you have all the elements. The red line is observed value, that is the experimental value, and the black line is for calculated value. And in most cases, it is completely overlapping to each other. Okay, and this is for the conversion of metal from 0 state to 2, starting from titanium to Zn. Fine. Any doubt? Next, we will see the trend for when you are converting M2 plus ion to M3 plus, or you can say M3 plus is accepting electron and it is converted to M2 plus. So these values, that is E naught for M3 plus aqueous, M2 plus aqueous in volt, all these are given here. So all the elements are not present, some elements are there. Now we will, though it is really difficult to give explanation that why some are very negative, some are very positive, but at least we can try. Okay. So see, for Mn the value is highly positive. So what it means? It means when manganese it is in Mn2 plus state, it cannot, that is, if you want to convert it to M3 plus, you have to remove the third electron, but removal of third electron is very difficult, and that is why the value is so much positive. But why it is difficult? It is difficult because Mn2 plus is already achieved stable half field configuration 3d5. But if you are removing further one more electron, that is a third electron, you have to break the stable configuration, which is difficult, and that is the reason conversion of Mn2 plus to Mn3 plus is difficult, and the value is so much positive. So it will not lose the electron very easily. Next, comparatively low value for iron. Now for iron, compared to manganese, it is low, right? So why it is so? Because now when you are converting Fe2 plus to Fe3 plus, basically you are moving from 3d6 to 3d5. So basically you are moving towards more stable configuration. So that is why now it is comparatively low value, though it is still positive. It is not that the conversion is very easy. It is still positive. That means reduction tendency is not there. But compared to Mn, relatively it is easier. Then again, so see, each case we are saying comparatively. So it is all relative. Okay. Low value of vanadium. Now it is very negative value, minus 0.26. It is related to stability of V2 plus ion. Now in this case, you have to consider crystal field splitting. So when it is V2 plus and normal vanadium, that is neutral, it is 3d3 4s2. So when it is V2 plus, basically these two electrons are lost. So V2 plus is basically 3d3, and if you consider T2G and EG configuration, then 3 electrons are here, which is stable half field configuration for T2G, T2G3. So this stable half field configuration, because of this comparatively low value of V is related to stability of V2 plus ion of, that is due to half field T2G3 energy level of 3d orbitals in octahedral crystal field splitting. Okay, so when you are trying to make V3 plus, basically you have to break this value, which is not also very easy process. Okay, now next we have the question here. Four successive members of first row transition elements. So what are the members? Chromium, which is having atomic number 24, then Mn 25, iron 26, cobalt 27. So that is it is successive. Successive members of first row transition elements are listed below with atomic numbers. Atomic numbers are given. Question is, which one of them is expected to have highest E naught value for M3 plus M2 plus? Now this is actually memory based because there is no direct logic based on which you can understand which one of them will be having highest E naught value. But as the table is given here, you can understand that maximum value is for cobalt. Okay. Now, if it is asked that why this value is so much positive for cobalt. So see, for cobalt, the electronic configuration is 3d7 4s2 when it is neutral. When it is 2 plus, 3d7. When it is 3 plus, it is 3d6. Now, conversion from cobalt 2 plus to cobalt 3 plus, it is difficult. But from the electronic configuration, there is no such logic based on which you can explain it. That is, when you are moving from 3D7 to 3D6, why this process is difficult? There is no direct answer. And that is because all these E naught values, they are actually dependent on so many different factors. That is sublimation enthalpy, hydration enthalpy, ionization energy, as you can see in this table. So overall effect is such. So just from the electronic configuration, it is not always possible to give explanation that why some systems are having very high value, some systems are not having very. So it is simply memory based question, and maximum is for cobalt. And another question may also be asked that you have to arrange according to order. So here maximum value is for cobalt. After cobalt, the next maximum value it is for manganese, 1.57. After manganese, among Cr and Fe, it is iron and Atlas gold. So this is a trend, that is from high value to low. Okay. Into
No, ma'am. No, ma'am.
okay. Trends in stability in higher oxidation state. Now, how the oxidation states are that we have already in case of oxidation state trend, that is different slide we have already discussed. But here especially we are focusing on the stability of higher oxidation state, because for D block elements higher oxidation states are observed, unlike S and B block metals. Now the highest oxidation state for the metals you will find only in case of halides and oxides. Now why it is so? Because halides, that means halogens, FClBr, and oxygen. So these elements are the most electronegative elements in the whole periodic table. And when we are talking about high oxidation state, basically just consider any one of the oxidation states. Suppose it is +5. So you have to remove 5 electrons. So it will be easier process when the other element with which it is making compound, that is with which the metal is making compound, if it is very electronegative, it will be helping to achieve this oxidation state easily. So that is why here only with halides and oxides you will find the highest oxidation state. So see here different oxidation states are mentioned. When it is +4, these are the corresponding metals in different compounds of halogen, TiX4. So when it is simply X, it is actually possibilities are fluorine up to iodine. Now see here it is mentioned VX41, that means up to bromine, not iodine. When it is X2, that means only F and Cl. When it is X3, up to iodine, starting from chlorine up to iodine. So different here superscript are mentioned over X, from which you can understand this. But here you can see only halogens are present, not other elements. So this table, these stable halides of 3D series, only halides are present. And another table C, which is for oxides, stable oxides of 3D series. Okay. So all these highest oxidation state that are possible for oxygen, and for each oxidation state the corresponding examples are given. So the ability of oxygen, why it can stabilize high oxidation state, it is even stabilized oxidation state which is exiting that of fluorine also, because oxygen, it is not only electronegative like fluorine, but it can also form multiple bonds. See this example, how many multiple bonds are there, I mean double bonds. Okay, so Mn forms highest fluoride which is +4 oxidation state, but fluorine cannot form multiple bonds. But with oxygen now it can achieve even +7. Both are actually high oxidation state, +7 +4 both are high, but compared to +4, +7 is more high, and +7 you can achieve only with oxygen, Mn2O7. So this molecule is Mn2O7. So this is because of the tendency for oxygen to form multiple bonds, which is not possible for fluorine, though it is more electronegative than oxygen. So that is why highest oxidation state that is possible only with halide and oxide. And among halide and oxide, if we compare, mainly oxygen will be helping to achieve the high oxidation state. Fine. Any doubt? Any doubt regarding all the slides? Because we will
No,
end the
ma'am.
session. So, thank you for listening. We are ending the session.